Okay, so let's look at the second part of this video. The original question was to solve this heat equation, right? We have a rod with a certain temperature and a PDE with some inhomogeneous boundary conditions on the space-like variable. Okay, what we did was we introduced theta related to the original u, the original target function. We change our target function. Right? We change our target. We have a secondary target first before we. So this is our primary target, but now we introduce a secondary target. Then we solve this first, and then we just relate that back to u. Okay. With this definition, with this change of variable, we have the domain is unchanged, the PDE is unchanged, but the boundary conditions is changed. Okay, so the initial condition definitely changed, but more importantly, the boundary condition for the space-like variables are now 0, 0, which is the Sturm-Liouville type of boundary conditions. Okay, so we talked about the strategy now is to solve this first and then get ux. So let's continue directly. Once we wrote this, what is the next step? Well, we do separation of variable. Okay, so now we let theta x equals to capital X of x, capital T of t, right? So this product of the two functions. So now the new PDE, if we want to specify the PDE for theta, now implies xt with time derivative k times xt with a double x derivative, and now the x is not going to be differentiated with t, only the t is differentiated with t, and k, the x is going to be differentiated twice. This function is going to be differentiated twice. This is not going to be differentiated. Now you can divide both sides by xt and get t dash over t equals to k x double dash over x. And since this is purely a function of t, this is purely a function of x, we can equate this to a constant, and we'll define this as lambda, give it a name, right, lambda. And now this breaks up into two equations. We break up into t dash equals lambda t, or and k double dash equals to lambda over k times x. So here we have an exponential equation. Here we have a simple harmonic equation. Okay, right. So we'll now also the boundary conditions. So the boundary conditions will now be changed as well. So let's look at this first for x, right? So x of so over here we have x of 0, t of t equals to let's do them one by one. Boundary condition 1, we'll start with this, is x of x and t of 0 is equals to 2 minus 4x. Okay, fine. All right, good. And then here, boundary condition 2, we have x of 0 and t of t equals to 0, which implies x of 0 equals to 0. And boundary condition 3, x of L, or x of 1, and t of t equals to 0 as well. Right, so I'm just breaking this out with our ansatz over there. It's equal to 0, which means x of 1 is 0. Okay, because t of t cannot be 0. Otherwise, if t of t is 0, this is trivial. We don't want trivial solutions for our PDEs. Okay, so can you see now which one is a Sturm-Liouville type? Well, we like I mentioned in class, we always want to start with a not always, but a general rule of thumb, and most of the time it works, is start with the space-like variable. So this is a space-like parameter. So we'll start with equation 2. So let's mark this down. Okay, and so equation 2 is now would basically be a simple harmonic equation. It depends on what lambda is, and because of these boundary conditions, the boundary conditions of 2 and 3 will imply the lambda larger than 0 and lambda equals 0 cases gives x of x equals 0, which leads to a trivial result. Okay. Because if this is positive, then you will get exponential or hyperbolic functions, which is impossible to match these two boundary conditions. If this is 0, you get a linear function, which is 0. So maybe let's actually write this out. So 2 implies the solution for x, general solution of x depends on the sign of lambda. So if lambda is larger than 0, then x of x is equals to maybe a cos square root of lambda over k, x plus b sinh lambda over k square root, like that. If lambda is 0, then x of x is just a linear function. And if it's less than 0, then we get a trig function like this. Okay, and we notice this case and this case would imply this equals to 0 by the boundary conditions 2 and 3. So this would be a trivial result. Therefore, we just focus on the trig solution with like that. Okay, so now we can apply the boundary conditions just like normal ODE from here on. Just basically solve for x or for t, and then you get theta. But at the very end, just remember to relate that back to u as your final answer. Okay, so there's a lot of algebra coming forward, just a heads up. But all the steps are, it's just algebra. The big picture it should be clear. Okay, all right. So yeah, continuing focusing on this. Okay, boundary condition 2 is x of 0 equals 0, right? Okay, so what's x of 0? X of 0 is e times 1, and we want that to equal 0. Of course, that means e is 0. Boundary condition 2, boundary condition 3 is x of 1 is 0. Okay, so that means now e is 0, right? So what is x of 1? X of 1 is f sine square root of minus lambda over k times 1, and we want this to equals to 0. So either f is 0 or the argument over here should equals to multiples of pi, integer multiples of pi. Of course, f equals to 0 gives you trivial solutions for x, which means trivial solutions for theta, which is not good. We want some non-trivial solutions for this PDE. So we just left with this. Out of all the variables over here, the thing we want to solve is lambda. So lambda equals to n pi and whole thing squared multiplied by k and multiplied by minus sign. Okay, so these are your eigenvalues if you want to define them as lambda n. Okay, but yeah, so these are your eigenvalues. How about the eigenfunctions? So therefore, the general solution for x is equals to f times f is not 0, so f times sine of square root of this is basically just n pi. So we have n pi x like that. Okay, so that's the general solution for x. And for theta, right? It's the you need to multiply this together. So you need to multiply. Well, this was x of x times t of t, but because there is multiple solutions over here, then you want to do a linear combination. But before we do that, let's solve what is t of t first. Okay. So we go back to the equation 1. Okay, so we go back to this because this is solved. So here, equation 1 would tell you the solution is, well, let's copy this out first. It's this, but now we know lambda. Lambda is exactly minus k n pi squared. Right. So it's that. Yeah, let's plug this in last. Let's directly solve this first because this is clearly there's an exponential function. Okay, with any constant. I think I've used A, B, C, D, E, F. So let's get to G over here. Yeah, so we know what lambda is. So lambda is minus k n pi squared t. Okay. So now we need to find these remaining constants. So let's piece this together. Therefore, theta of xt is going to be, there's a sine n pi x term, there's an e to the minus k n pi all squared t term, and because this depends on n, so we just sum over some general constants. We can group the g and f or whatever together, okay, to that. Now, where should we go? Technically, n can span from minus infinity to positive infinity. However, this is an odd function, so all the minus parts just collapses together with the positive ends. If n is 0, this is trivial, so this whole thing becomes 0, so we can directly just start from 1 without loss of generality. Okay, right, so finally, of course, the final answer is u, but before that, let's find the k first. Okay, so we need to solve k. We apply the last but not least boundary condition number 3. Boundary condition number 3, what was it? Let's try to remind ourselves. It's saying x1 t, sorry, boundary condition 1 is x of x and t of t is equals to 2 minus 4x, right? Basically saying theta of x, sorry, x of t equals to 0. Basically saying this equals to that. Okay, what does that mean? Well, we have this already. Let's apply this in here. So sum from 1 to infinity, kn sine of n pi x times 1, because we plug in 0 and we want this to equals to 2 minus 4x, right? So now we can do the classic thing of projecting out the kn's with orthogonality. So we multiply by the orthogonal combination over here. So on both sides, we integrate dx and multiply, well, we first multiply by the orthogonal combination. So that's m pi x equals to 2 minus 4x multiply sine m pi x and integrate both sides by dx. Okay, so we apply this and this on both sides. Oh, I forgot to copy the sigma. Okay, where do we integrate from? We need to integrate from the domain that this is defined. This is defined between 0 and L, right? So we need to apply that over here. Okay, so we can start with the left-hand side. The left-hand side is very standard. So the left-hand side is, let's pull out anything that has nothing to do with x. We just get this, the x of sine n pi x with sine m pi x. Okay, so you recall this is even integrand, so that is basically half of integrating from -1 to 1. Because the integrand is even in x. And now this is equals to, use the identity of the orthogonality for sine n pi x over L and n pi x over L. So that gives you 1 delta nm. It gives you L delta nm, but L equals to 1 over here. Okay, so the whole thing multiplies over here, will collapse. So let's actually write it out one more step for clarity. Equals to 1/2 delta nm. So now every single term from 1 to infinity will be 0 except for n equals to m. So we're left with km and 1/2. Okay. And the right-hand side of this is, so when we got to here, the right-hand side of this is literally just need to do this integral. Okay. 2 minus 4x sine m pi x. Okay, so you do this integral, find k. Again, let me talk about the big picture. You do the integral, find k, and then you and plug that into the general solution. You've got theta, and go back to u, remember. Okay, so let's actually do this algebra, but I just want to emphasize that this is just algebra. So I'll just change a slightly different color. Okay, so we can do an integration by parts. We can see if we can do this all together. If we let u equals to 2 minus 4x and dv equals to sine of m pi x dx. Du is going to be minus 4 dx. V is going to be integrate this. So we have minus cosine m pi x and minus 1 over m pi in front. Okay, good. So it gives us the right-hand side integral will give us integration by parts, right? So we have u, so 2 minus 4x times v, so minus 1 over m pi cos m pi x going from 0 to 1 minus v du, so we have minus 1 over m pi over here and integrate 1 and we have cos m pi x and we have minus 4 dx over here. Okay, good. So now we have plug in x equals to 1 over here. So first of all, let me pull out the 1 over m pi from the square brackets. 2 minus 4 is minus 2 and cos m pi 1. Okay, minus 0, plug in 0, I get 2 and cos m pi x is with x equals 0, it's just 1. Okay, so that's what's going in the square brackets. And then here I have 3 minus signs, so overall it's minus 4 over m pi integrate 1 over dx cos m pi x. Okay, so now I have let's factor out the 2 as well. So I have minus 2 over m pi from the square brackets, and I have cosine m pi minus 1, but cosine m pi is minus 1 to the m. Okay, we're familiar with this identity. Minus 1, okay, and minus 4 over m pi, and integrating cosine gives you sine with an extra factor of m pi. So let's put a square over here and have this as sine m pi x evaluated from 0 to 1. Sine of 0 is 0, so we just have to do the top one, which is sine of m pi. But sine of m pi is always 0 because m is an integer. So yeah, so we out of these two terms, actually both of them gives you 0, and we're left with let's flip the 2 to the positive, and we'll flip the order of this like this. Okay, good. So now we match both sides together. On the left hand side is km. So we have, when we match these together, we have kn is equals to twice of the right hand side. Yeah, so we'll have 4 over n pi. I'll just change the m's to n at the same time, minus this. Okay. So if you want, this is also if you like, we can also check if n is even number. This is going to be 1, so it's going to be 0. So this is going to be 0 if n is even, and if n is odd, this would be this would be yeah, minus 1. So 1 plus. So you have 1 plus 1, so that's 2. So we'll have 8 over n pi if n is odd. So basically just twice of the coefficient. Okay, so if you want to visualize it that way, that's fine. But anyway, this is not necessary. If we therefore have the specific solution for theta. Okay, so the specific solution is now going from 1 to infinity and 8 over, well, either way is fine. So you can either write it like this, 1 minus this, right? And have the sign n pi x and the e to the minus, remember k was 4, so n pi square t, like this. Yeah, so that's one way to write the solution, or if you want, you can just write the odd terms. And then you will just have 8 over n pi sine n pi x e to the minus 4. So we're just summing the odd terms if you want. Either way, that is fine. Now, is this done? Not really. We still have the u. So we did, but that's easy because this is just, right, 4x minus 1 is the u steady plus theta. So plus, let's use the first one so I don't have to write n odd. In fact, let me pull out the 4 over pi as well. So it's just write out the step. It's u steady of x plus theta of xt, which means it's 4x plus 1, 4x minus 1 plus 4 over pi. We'll pull that out since that has nothing to do with n. And we have 1 minus 1 to the minus 1 to the power of n over n, right, times sine n pi x times e to the minus 4 n pi square t. Okay, so that's your very final solution for u. Okay. Okay, so that's the complete solution with all the workings. Lots of talking, but if you write this out, it will be a little bit shorter. Anyway, let me know if you have any questions. Otherwise, hope this is helpful and good luck.